for each evaluation.
You don't know the kills again.
And then like online, each one I finished it. He's a failure of a teacher. Last one so everything is different for each one.
Sometimes, yeah.
Yeah, that's what they're doing.
I mean, I would if I could.
Yeah.
Okay, homework there.
I got $80,000 more dollars.
There's corrected homework.
I thought it was pretty funny. Like,
I know.
Like his lectures never change. Like,
I already got it.
Can't do that in the phone.
from last.
But I didn't want to do it. If I keep doing this, no. Hi. Thank you.
Do not get home.
Wow. I just thought it was hilarious when like he would come up with he would have a lecture that would and be like written on the lecture. It's like this is a mistake. It should be like negative 5. It's like that's an lecture. It's like why did you write on the lecture saying the whole thing is a mistake? It's like rewriting the problem. Like when you teach it to us. Like yeah, like mainly just like scroll to the PowerPoint. It's a shame that he like is in complete control of like
Yeah, it's just completely
major.
Yeah.
Some people like waited for that.
8.
I was like, it sounds like
Actually, I forgot to bring the solutions to your homework problem. I'll just have to hand them out a little later, or I'll put them in the box outside my office. Pick one up. I'm a little cold. I handed out the homework for Wednesday. You notice no written homework. Just reading, and that reading, if you do carry it out, is going to be well ahead of my lecture. So read it with, and then there's a lot of complicated looking symbolism there. And I commented, don't get hung up on the math. And think about like, what are we trying to do here? So we'll eventually get to that detail business in the lecture, all right? And I'm reminding you that we have a session tomorrow at 12 o'clock to 1 o'clock, hopefully in this place. But we're going to meet someplace around out there. And if this is busy, well, then you have to go someplace else. So I don't know what the schedule is for this room.
It says 1 to 2 on this paper.
1 to 2?
I think it's 1 to 2.
Oh, 1 to 2. Okay, 1 to 2. Stop there. I have all kind of choices. Okay, 1 to 2, and like I say, meet out there. And if this room is empty for that hour, then we'll meet in here. Otherwise, we might have to meet across the hall. And then, of course, the quiz is on the next day, and it's not going to cover today's lecture. It's only going to go through Friday's lecture. And I mean, really, what I mean is dielectrics, you know, okay, instead of now D is equal to epsilon 0 E, it'll be D is equal to epsilon E, where epsilon can be different by some factor epsilon R, relative dielectric constant, from epsilon 0. And the idea of capacitance, and then the energy stored in the capacitor, as you could get it 2 different ways, right? By the whole thing, or by getting a density of the energy here, and integrated over the volume of the capacitor. That's the kind of stuff that I would like to, I haven't made the problem up yet, but that's the kind of thing I'm going to do. It may be a combination of, you know, energy and capacitance, like the, all right? And don't forget, it'll be at the start of the class lecture, so don't be late. All right, at last lecture we were, well, really, you know, there's electrostatics, and then there's magnetostatics. Electrostatics has charge as its source, and we don't say very much about that charge. We don't really, to tell you the honest truth, I don't think we really know what a charge is, but we do know it has effects. And so we talked about those effects as being a tensing up of the universe and electric field, and then went all the way through this electrostatics. Well, magnetostatics, the source is not a charge, but a charge moving, and for us, for static fields, moving at a constant velocity, we call it DC current. So basically the source of the magnetostatic world is going to be a DC current flowing. Of course, how do you get that current flowing? Well, you got to put a voltage across some kind of conductor, and that's why we had this interposing chapter, this interposing stuff on conducting material, a gas where the positives and negatives aren't tied together by an interatomic force like in the dielectric, but rather they're free to move the minute they see an electric field. So, and that's what we would call current. And in our particular case, we're going to ask that current to be DC current, constant velocity current. And that's when we had to discuss the things like conductivity and energy lost into heat and things of that sort. So I'll just sort of re-summarize that stuff. I didn't do a very good job last time, I don't think. If we have some of that kind of stuff, so now we have two different kinds of stuff now. We have stuff that is described by its ability to store energy. Do you remember that? Epsilon has something to do with that spring. Springs store energy. They don't lose energy, I guess, pretty much. And now we have another thing which tells us how the stuff heats up. In other words, current flowing through a conductor. And those are the two ways we describe. Well, there's going to be a third one. We're going to call it mu. But that'll have to do with the magnetics. The magnetics stored energy. This is electric stored energy. And let's say we take a couple of very good, let's say, copper metal plates. I'm really forming a capacitor. And we fill it with this stuff. And in particular, let's say we're trying to, we know about this. We're trying to talk about this stuff. So let's say, oh, I put a positive here and a negative here. How do I do that? Maybe put a battery or something across like that. Anyway, I got positive charge and negative charge, which causes an electric field, E, across here. And of course, there's a D also, and the D is related to the surface charge density and all that jazz. That's all that we know about. Now, this E is affecting the charges, and they're free to move. So we have pluses and we have minuses. Now, what's going to happen is the minuses being much lighter. I'll draw it like there's a typical electron. The negative is going to go in the opposite direction of what the E field direction is, right? I mean, the positive, that's the way we define things. A positive charge will go in the direction, have a force on it, in the direction of that force field called the E field. But the negatives will go in the opposite direction. And remember, I talked about the fact that these negatives, and that's just one, there's Avogadro's number's worth of those things bumping into one another, and that's what's going to cause the heat. And therefore, these things don't go at the speed of light. They bump into one another, are slowed down, I say, by about 5 orders of magnitude from the speed of light, and they are causing essentially a current. Now, the way Benjamin Franklin defined current direction was with positive charges. Well, we know that it's really electronic charge that's moving. So basically the current, and maybe this one I should emphasize by giving a little color here, the current is flowing in the same direction as the E field. In other words, the positives, that would be the current as we define it. Well, the real current is being caused by these guys here, but we still define it in this direction, right? And now when I say current, I don't really mean current, amperes. I mean amperes per, let's say, draw a little surface here, amperes per going through my hand. and a different number of amperes going through my hand here, and a different number of amperes going through my hand here, if you wanted to know how much current was flowing through this whole region, hand after hand after hand, you would have to integrate. And what would we call that? That's what we would call current density. Now, I don't mean, it can't be per volume. I mean, current amperes per meter cubed? No, amperes per window, basically, amperes per square meter. So we call it J. Now, that's comparable to what you know as current, but it's not current amperes, it's amperes per meter squared. All right, like that. And then, so for example, I have so many amperes per meter squared flowing here and different here. I would have to integrate across this whole thing to find out how many amperes were really flowing to here, and therefore how many amperes are flowing around. You understand what I'm saying? So this is what we call current density. And without belaboring the point, I came up with an equation that says that current density, amperes per meter squared here, is equal to a constant, and well, I'll call it sigma at this point, times the electric field. So if I, for example, put twice as much voltage on, keep the distance the same and everything else is the same, but just drive it twice as hard, I get twice as much electric field. If I get twice as much electric field, the forces on these guys are twice as big, and therefore the current, or the current density, is twice as big. So it's proportional to the E if this is a linear stuff. Again, nothing is truly linear, but let's say that's a good approximation for us. So I see an E that is driving the whole thing, and that, what is it driving? These electrons, and we measure that in terms of current, or in this case, current per meter squared, current density. And the relationship between the two, that constant between the two, is the conductivity. Conductivity. And if you recall, you could kind of split this up playing around. I do it in my notes, I won't do it here. You could describe it as rho E mu E, where that conductivity has something to do with, well, how many electrons are there per unit volume ready to move, to cause, if there are none, then of course you're not going to, and that's the case with dielectrics. They aren't going to be moving, and there aren't very many, in an ideal one, no charges ready to move. So basically the conductivity is equal to 0, and there ain't no current no matter how much E field you put across there. That's the idea of the strict dielectric, where this guy isn't even here. By the same token, if you have lots of them, but they're not very mobile, I mean, they're just sort of stuck in place, you know. And why would they be stuck in place? Basically, their things might be so dense that they can't move. So this is the mobility of electrons, and this is the charge density of the electric, well, the electrons in this case. And if you put the two together, and I did that in my notes, you wind up, rather than write it that way, you write it as the conductivity, the ability to conduct electricity. I mean, you know, you get that feeling, conductivity. I mean, not conduction, but conductivity, the ability to conduct electric charge, essentially causing a current, or in this case, current density, okay? Like so. Now, that's sort of comparable to D is equal to epsilon E. Remember? Now, that's the same thing. This E is the guy that drives everything. Well, how should I say it? That E is really driving everything, but of course this guy depends on, you know, how hard did I, what kind of voltage did I put across here? But he's really the guy that's driving this, so it's fundamental. And this D is now the electric flux density, but this is not, remember, this has something to do with the springiness of the stuff. So if it stretches a lot or stretches a little bit, that's what this is telling me, the atoms that are hooked together. That's what this is telling me. And as you know, if you stretch a spring, and that's what we're talking about here with this force, if you stretch a spring, you're storing energy in the spring. You're not giving up heat. Let's say the metal is a perfect metal. There's no heat that goes up when you stretch the spring. Then basically you can get that energy back again, right? You know that if you took a spring and hooked it, let's say here and here, 10 years later you can come back and you'll find that you could kill yourself with that thing if it got unhooked, right? There's energy stored in that spring. That's what this is all about. So this is energy stored in this field, and this thing is the heat that goes up. So this is the comparable thing. Now, what they do is they call this equation and this equation, there's going to be a third equation when we get into magnetics, they call those the constitutive relationships, like the Constitution, that comes from the same word, how this thing is made up, I mean, how it's constituted. And they call these the constitutive relationships. This one tying the stored part of the Constitution, and this one the heat loss. And if I recall, we went on from this and we talked about energy stored. Well, energy density. Remember that the energy, this is the little w of the electric source, there's going to be magnetic too, was 1/2 epsilon E size of it squared. Remember that? This one, you can talk, I didn't prove this in lecture, but I do it in my notes. This one, there is power lost to dissipated. I guess I call it P sub D or something like that, which is equal to sigma E squared. Something like that. And this is in watts per meter cubed. How many watts? And this is heat. Heat in the volume. Well, no volume here, at any point. And if you want to figure out how much heat is lost in the whole thing, then you have to integrate over the volume of the whole thing. Here, same thing. This is in joules per meter cubed, and if you want to know how much energy is stored in the whole thing, you integrate over the volume. And that was one of your homework problems, if I recall, to know how much energy was stored in a capacitor using the field technique, where you integrate the energy density. Okay, what else do I have to say? Now, at this point in my notes here that I wrote this morning, I want to talk about the dimensional analysis, or whatever you want to call it, of these two equations. Okay, in other words, I have units for this. What is this known as? Volts per meter. What is this known as? Amps per meter squared. What are the units of this thing? What do we, we call it conductivity, but what are the units of that guy, right? And then same thing here. This fellow here is volts per meter. This fellow here is, what was it? Coulombs per meter squared, huh? Coulombs per meter squared. So what are the units of this thing? That's the sort of thing that I want to talk about. And in particular, let's say, which one should I do first? Let's do this one first. So that's what I do. If you go back to your circuits, now in circuits you didn't talk about electric fields and current densities. You talked about voltage and current. That's what and what did you call it? Ohm's law. You talked about Ohm's law, right? So let's write Ohm's law. I mean, you can write it many ways, but I'm going to write it this way. Now G is 1 over resistance. Voltage is equal to I. Now the way you know it is voltage is equal to IR. I mean, that's probably the simplest way. But this is more comparable to, the way I wrote it there is more comparable to this equation here. So this is Ohm's law. This is nothing more than Ohm's law. This one is really, it's a comparable thing. This is in amperes per meter squared. This one is in amperes. This one is in volts per meter. This one is in volts. This, if you recall from your circuits, is the conductance. Huh? You call this the conductance. If you take 1 over the conductance, you get the resistance. So this is known as the resistance. Like that. Now, if we make an analogy here where we say, okay, ampere, if I have conductance times volts is equal to I, and then I divide by meters squared, basically, I can see volts per meter, meters squared, volts per meter, that goes into the electric field. So what's left over, and on the left side now I have J, really amperes per meter squared. What is G? G is essentially conductance per meter, right? That's what this, I shouldn't say G, that's what this fellow is, conductance per meter. So what's the conductance? It's Siemens. Siemens per meter. Those are the units of conductance, conductivity. Siemens per meter. And Siemens was a German engineer, and in the old days we used to call that resistance was called ohms, and then 1 over the resistance, the conductance was called mhos, ohms, and then written backwards, mhos. They don't do that anymore. That's the old-fashioned way of doing things, mhos. They call it Siemens, named after this German engineer. So this is in Siemens per meter. Now, if we do the same sort of thing here, in this case, I have, let's say, energy in a capacitor is 1/2 CV squared, right? Now, again, this is in joules. This is in farads. This is in, well, volts squared, huh? Something like that. Now, this is in coulombs per meter squared. This is in volts per meter. And the question is, what are the units of this fellow here, all right? I think that's right. So we have, in this case, joules, joules is equal to farads times volts squared. Let's see. This one is volts per meter, and then the question is units of epsilon 0 is equal to joules, and joules is this 1/2. Oh, it's this thing here. So it's farads times volts squared. Okay. Farads times volts squared. So what are the units with that? And I have farads here, and the units are epsilon 0 would be farads per meter. This is per meter here. So the units of the epsilon 0 is, strangely enough, epsilon 0 is in farads per meter. And that makes sense, actually, in some way, because this represents stored energy, this is heat loss, so this has something to do with conductivity, and this one has something to do with energy stored. Where do we store energy? In a capacitor. So all this is saying is a very important idea that we started at the very beginning when we talked about Coulomb's law. Remember, we had a 4 pi epsilon 0 there. What the hell was that epsilon 0 anyway? Now we're finally finding out that what the epsilon 0 is, measured in farads per meter, is the ability of empty space, not even stuff, empty space, no atoms, no nothing, to store energy. That's kind of interesting. And this is why the field concept is so amazing, because, and it makes sense. The analogy I always make is the sun is a source of electric field, magnetic field too, but let's say electric, and if you shut the sun off, let's say you shut the sun off for some reason, do you really think that down here on Earth that the sun would essentially blink out? No, it takes time for that light, which is electromagnetic wave, to reach the Earth, what, about 8 minutes, something like that. So for 8 minutes, the sun would be warming up your hand, and then it would blink out. Well, where do you think all that, where is that warmth coming from? It's not coming from the sun, it's blinked out now. It's coming from the energy that was stored in the space between the sun and here. It's stored in this epsilon 0. That's where it's stored, in empty space, all right? I mean, that's living proof, basically, that the field stores energy, and that for 8 minutes, that energy is being dissipated here on Earth, all right? If you were even further away, it would be a longer time that energy would be coming at you, all right? So that's what epsilon 0 is. It is the ability of empty space to store energy. Now, electric energy. Now, when we get into magnetics, there's going to be a thing called mu0, and it's going to be measured in henries per meter, like inductance. See, this is like the capacitance of space. This one is going to be like inductance of space. It's going to lead us to the idea that even empty space. Now, dielectrics, same thing, only even more so. But even empty space, you can represent by an inductance and a capacitance per unit length. Boy, if that doesn't remind me of man-made transmission line. That was a model for a little length of a man-made coax or something like that. Remember? An L and a C. Well, an L prime and a C prime. This was essentially the inductance per unit length. Holy smokes. And this was the capacitance per unit length. Holy smokes. Basically, empty space is not, this is a representation for empty space. Now, of course, a long length of empty space would be another one, and another one, and another one. And then, of course, another one, and 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 another one. You know, three-dimensional transmission line, fancy-dancy, but much more elegant than the man-made transmission line. But you see, that's what I meant when I said that when I get into transmitting waves in the dynamic field case, it's really going to devolve to something like this, only instead of talking about L's and C's, we'll be talking about mu0 and epsilon zeros and things like that. Or if it's in material, it'll be a mu and an epsilon, which are different from epsilon 0 and mu0. Now this is yet to come, that we have this. And then of course, don't forget, what if this stuff, this so-called empty space, like a foggy material or something like that, what if it's lossy? Well then, don't forget we had an R, well an R prime, and we also had a G prime. We've already been talking about the G prime as being an analog to the C. Remember that? I mean, I talked about that at the last lecture. This G and this C are analogs of one another. So, and that's the full model of lossy stuff. I mean, in this Mother Nature's transmission line, being lossy two different ways. And we consider it to be like R prime and G prime, copper loss and dielectric loss. And we'll get to that when we get into dynamic fields, this model. I mean, and once you got that model, the equations are the same as we had for man-made transmission lines, just that we'll be talking about mu's and epsilons instead of L primes and G primes and, you know, all that kind of stuff. So, but it'll be the same thing, and we can go kind of quickly because those equations you know the solutions of already for man-made transmission line theory. Okay, well, that's the beginning of this intervening chapter. There are a few other things there. One of them is, hey, what if I used to have a region 1 and a region 2, and an epsilon 1 and an epsilon 2, two dielectrics slapped together with a E, let's say E1 and a D1 and an E2 and a D2, and I found out what the boundary conditions were. Normal D jumps by whatever surface charge density of the free sort. You rub it. No, so you have to do some work to put this stuff on there. But now we have that third thing. If there are some free electrons ready to move, that means that this is not just pure dielectric. This one has a little bit of conductivity. There are some free ones ready to move. And how about this one? Well, maybe it too. This might be aluminum and this might be copper or something like that. Or a good dielectric and a little per dielectric. So this is different from this. And so this E field is taking those free electrons and moving. Oh, that's a J1. And over here, if this is conducting, this is a J2. So we have that third quantity, the J's, the flow of these electrons, which we know is current density in this case. Okay? And the same old thing with alpha 1 and alpha 2 and all that business. And now it's just like water. Think of DC current. This is DC. DC current like water. If I take a pipe and I put a certain amount of water in per unit time, because it's incompressible, the same amount is going to come out, right? That's the idea. It's incompressible fluid. Well, DC is kind of like here. Instead of this being a pipe, here's a copper wire. You put that much DC current in, that much DC current is going to come out. Right? It has to. It's not going to, you can't put 3 amperes in and a half an ampere comes out, or a half an ampere goes in. No. Whatever goes in has to come out. Like incompressible fluid. All right? So far, so good. Well, that means that if you take, I'm talking now about the J's. We have the boundary conditions on these guys. Tangential E is continuous. The D's jump by this thing and all that stuff. But now if you take the normal component of J, so there is the normal component of J1, normal. And then here is the normal component J normal of 2. Those two have to be the same. They got to be the same. It's just like in this has to be the same as that. Now, this and this are related by those conductivities and the E field. Don't forget there's an E field that's driving all of this. So there's an E field and a J relationship, an E field and a J relationship. These guys are related that way by that constitutive relationship that we just erased. Okay, but so the next boundary condition is the third boundary is J normal 1 is equal to J normal 2, always. And then you might say, oh, I remember that that E tangential 1 was equal to E tangential 2 independent of that rubbing business, rho surface free that you put on. The D normal 2 minus D normal 1 is equal to rho surface free. That wasn't independent. If you rubbed it, then there was a jump in the normal component of D. But I don't care how much you rub it, the tangential E's are the same. Same thing here. This is independent of rho surface free. It doesn't, you can rub that surface all you want, and the normal components of the J's are going to be independent of that, right? Now, that's not the way you actually put on a conducting sort of stuff, whether it's well-conducting like metal or a dielectric that's imperfect that has some of those free electrons to move. I don't care which one. You don't put this charge on by rubbing it. If you did, you could do that. But if you did, the minute that charge begins to accumulate on this surface, because it's lossy, it'll start to dissipate. It'll start to fade into the two lossy regions. That's what you can't and you got to keep rubbing it in order to keep the charge on here, because it keeps dissipating and going up in heat. Okay, so that's not the way you do it. That's not the way you get the surface charge density. The way you do it, I mean the way Mother Nature, you don't do it, Mother Nature does this, is she does it herself. What is current? Well, what is current density? It is the carrying of charge, right? It is charge that's being carried. Now, if you think of this interface now, let's say a copper to aluminum or a lousy dielectric to a little better dielectric, or however you want to think, but lossy stuff, this current that's going to flow is going to find, it's going to be impeded by this interface. Now, think about this. The analogy I want to make is this. Let's say I have a stream, a water stream. There's the water flowing. And in that business of incompressible fluid, as much water is flowing out as is flowing in. Doggone it, because it is water, not air, not compressible stuff, but incompressible stuff. And so if you had, let's say it's a stream, and you're measuring the stream flow here, and you're measuring a steam flow here, it's the same. Okay? The momentum of the water. Now let's say that along comes a beaver, and he builds a dam. So here it is. He builds a dam of some sort. And now the water is still flowing at that same rate. I mean, you know, that water is still coming from the mountain someplace, flowing at the same rate. But what happens is the water builds up. So if you compare it with this, it builds up to a higher level, and then it splashes over, and by George, the amount of water going in is equal to the amount of water going out after the dam has been filled up. In other words, not in the transient circumstance, but after a long time, steady state, then this water is equal to, it has to be. I mean, you can't have more water flowing in just because you got a dam there than you have here. It's the same as this, but you have this now level here and this level here, and this is called hydrostatic head. All right, this is like what they call hydrostatic head, which means that there is some energy stored there, and that is comparable, not exactly, but it's comparable to this. When the current is flowing, and the current is a charge carrier, the current flowing normal is equal to the current flowing out normal. So that means like the current in is equal to current out. But something is different if this is a different conductivity than this. It's sort of like there's a dam here, and you build up, not hydrostatic head, but you build up charge density on that surface. And if the current keeps flowing, after some time, it'll build up, and it builds up rather quickly in the case, this electrostatic case. It'll build up this charge, and then the amount of current flowing out is exactly equal to the amount of current flowing into that surface, okay? And that's comparable to the dam in the hydrodynamic case, hydrostatic case. And so this charge is built up by the very fact that you have current flowing. That's what builds it up. And if you can't disturb it. What I mean is if you say, well, how can I change that? Yeah, I suppose you could, so to speak, rub it some more. But again, what will happen is that excess will dissipate into the two lossy regions. This has to be the charge that is left on there if you have a current flowing under the impression of an electric field. And then you can say that the rho surface, I proved this in the notes, the rho surface free that is built up I think is equal to J, the normal component. And I don't care if you're talking about the normal component here or the normal component here, because they're the same. If you want to write it, you could say this is Jn, the normal component. They're all the same, so why call them 1 or 2? And this is equal to epsilon 2 over sigma 2 minus epsilon 1 over sigma 1. If it turns out that the ratio of the epsilon and the sigma in region 2 is exactly the same as in region 1, then this is, and you don't build any charge up. That just is a very special case. But in general, not so. I mean, if you have a big conductivity or a little conductivity, and even if these are the same, then you find that the amount of charge you build up is proportional to the amount of current you're forcing. Well, that makes sense, because if I double the amount of current, that means I'm shoving more charge in there, and more charge is coming out too. So that makes sense, but you have to prove that this is, and where do these come from? It comes from all these boundary conditions. I mean, and I do that in my notes. Okay, and then this is in coulombs per meter squared. So in the case of conducting material, you always have charge. Well, not always. If you have some special condition hold, then you don't have charge density, but in general you got charge density, and you didn't rub it. It is the current that is causing it, the current that's flowing across there. Okay, that's one, how would you say, a little addition using the boundary conditions. And that the nifty concept about hydrostatic head. All right. One other thing is what we call the equation of continuity. Now that we're talking about, like charges of the free sort, volumetric charge, and current, current density, are these related to one another? In other words, current is a flow of charge, so somehow there must be a relationship between that flow and the charge itself. That's called the equation of continuity, and I will show you that. And where does that continuity come from? It comes from almost a religious idea, in the sense of we take on faith the idea of conservation of charge. So another name for this is conservation of charge. That's the assumption that we make. That's the assumption that Maxwell made, that, well, we can't prove it, but we're going to say that the whole universe is neutral, that there's conservation of charge. It either moves from here to there, but you don't make it as you're moving it, or you don't lose any. So it's called the equation of continuity, or the conservation of charge, just like conservation of energy idea. We sort of accept that as a starting basis. Now, what's the thought process behind this that leads to the equation that I'm going to derive? Let's say I take a volume, V, surrounded by S, here's S, and in there is Q free. Now, of course, you can say the charge density is stronger here than here than here. Then integrate it over the whole thing, you get that many coulombs. So, or you can describe it by rho volumetric free. We know that, right? You integrate this stuff over the volume of interest, then you get that amount of charge. So I don't care if you're talking about this or that. Now, the way I'm thinking, I should really dash this thing, because I'm not really thinking of it as like a piece of metal or anything like that. This is just a thought experiment. Here's the region. Here's the surface right here. I mean, I just made it. All right. Now here is this Q sub f. Let's say they're, just for the hell of it, let's say they're positive. What do positives like to do to each other? Escape. They like to get away from one another, right? So let's say that's what's happening, that this charge is coming out of this surface. And I can picture it like this and that and that. And maybe over here, actually, they're coming in, and over there, they're going out. And as usual, I will define the normal to the surface like that as outward from the kidney-shaped surface, okay? Like that. Now, I'm going to change a little notation here because if you talk about current density, that's amps per meter squared. And I'm thinking of that as being DC. Well, in this case, think about it. Here's this charge. Right now, there's 17 coulombs in there. 1 second from now, there's 16 coulombs. And then 1 second from that, there's only 14 coulombs. And in other words, this is changing with respect to time, like that. So actually, because it's kind of like a balloon that has punctures in it, little holes, and the air is puffing out in all directions, and less air is in now than there was, an hour ago, and less is going to be in the future. Do you understand what I'm saying? It's kind of like that. So if you want to, you can sort of think of as a function of time, the QF as a function of time is doing something like this, right? It's not, you're not pumping it in, it's coming out the way we're thinking about this. And as a matter of fact, therefore, the slope of this guy is negative, all right? The rate of change of Q, dQ free dt is negative, like so. I'll point that out later. But because it's this, the current that's flowing is this dQ dt, right? dQ free dt, or the charge density, if you want to write it that way. This is the current density. This is a function of time, right? Because this is a function of time. So you will find that when I get into dynamics, whenever I talk about the electric field that's changing with respect to time, or the B field that's changing, or the current is changing with respect to time, I don't use this symbol. I use this symbol. Scripty kind of stuff means, oh, that's a function of time. And of course, you can kill the lily by saying, oh, it's a function of time. This one is not. This one is independent of time. It's the static field. Well, because things are changing with respect to time, instead of using that symbol, I'm going to use like that symbol. This is just a refined thing. That's a function of time, like that. And there he is there, and there he is there, and all the way around there's this J as a function of time. And of course, I've ignored it, but it's a function of position too. I mean, maybe the J is big here, and it's bigger here, and it's smaller over here, and it's negative over here, going in instead of out, and all that kind of stuff. Do you understand what I'm saying? So I'll use this symbol simply because that makes it more close to what's happening. It's changing with respect to time. It's not a DC current anymore. All right, now with that, let me start the arithmetic. Let's say the current, the whole current. Well, again, I suppose that would be current, amperes, but I'll use that symbol because it's a function of time. See, the current that's flowing out. Well, how much current is flowing out? Well, I guess I would just integrate all the way around this S, all the way around here, this J as a function of time times ds. Well, is J pointing? Yes, J is pointing. In other words, it might be pointing like so. So really, that much is coming out. That the tangential component isn't coming. You got to write that as a underbar. And ds is, of course, is in the n hat direction and all that. So there's that dot product. That's the way you have to write it. That makes sense, right? That's the amount of current. This is in amperes. This is in amperes per meter squared times meter squared amperes that are flowing out of this surface, right? Now, what is this current? It also can be written as d dt of that Q, but that Q can be written as the volume surrounded by S of this rho volumetric, right? And it's technically a free sort, as a function of time, d volume. I mean, this is another way to write that current. It's the rate of change of Q, and Q can be written in this fancy way. This Q can be written as an integral over this whole surface. So that's the way I've written it, like that. Now, as I pointed out, ddt of this integral, actually, the Q, this is Q, the Q is getting smaller and smaller, and yet the current is positive going out. So you have, by convention, you have to put the minus sign in there. So this is another way to write it. And this has nothing to do with the fact, nothing more to do with than the fact that the Q, or the rho volume free, is getting smaller and smaller with respect to time. This is getting smaller and smaller with respect to time. You're taking a derivative, and so if you didn't take that negative, it would be positive. But you know that it has to be negative because essentially the charge is getting smaller and smaller and not bigger and bigger. So this is two ways to write the same thing. So this is equal to this, that means that is equal to that. So I won't rewrite everything, but let's say it's like that, equal to this guy right here, minus d dt of this thing. Well, now this is where a mathematician would probably throw up. I'm going to interchange the integral with the differential. That they don't like to do that. You have to prove all kind of stuff. But for us, this is not a pathological function of time or of space. I mean, it's physics. And so what we do is we interchange. We say, oh, I can take that differential inside. But by the way, this is the derivative with respect to time, and this is and I didn't write all this fancy stuff. This is a function of x and y and z and t. So what I'm going to do is when I'm doing the integral, I am going to keep the x and y and z constant while I'm horsing around on the t, and vice versa. I am going to keep t constant while I'm horsing around on the x, the y, and the z over the volume. So to make the long story short, maybe I could write this as the minus sign, integral, 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 all over this volume that is surrounded by S of the partial with respect to t, right? That's what I mean. Hold the spatial ones fixed while you're horsing around on the t of this rho volumetric as a function of t dv, right? So that's the way I would like to write it. And then therefore, I'll continue on here. This is the integral vs of this rate of change with respect to time of rho volume free as a function of time d volume, right? This is essentially the equation of interest. Now, those both happen to be equal to the current flowing out of the kidney shape there, but that's not of concern. It's this thing is equal to this thing. Now, if you notice what I have here, I have a surface integral and a volume integral. I don't like that. So what I want to do is I want to change this to a volume integral so that I can say a volume integral is equal to a volume integral. Okay? Now, what allows me to do that? What allows me to do that is what we call the divergence theorem. In other words, identically, this thing, this integral here, is equal to the integral all over Vs of not the j, but the divergence of j, and then times the dv. Now, where did that come from? I mean, this is called the divergence theorem. Actually, it's sometimes called Gauss's theorem, too, because Gauss devised this idea. Well, think about it. What is the divergence? The divergence of anything. I mean, here's anything. It's defined to be, take the integral around the surface of A dot ds all over the volume, the little volume that is surrounded by that ds in the limit as the delta volume punches down around the point. Remember that? That's the definition of the divergence operation. In other words, and the way I think about it, it's a little box that says how much of A is going out minus how much of A is going in per unit volume of box. That's the way I say it. But mathematically, it says do an integral all the way around the little box and divide by the volume. Now, if you think about it, what if I took this little dv here, put them over there? I would have del dot A times the dv is equal to the integral of A dot ds. Then I integrate this guy over the volume, essentially, and basically I have the same thing. A j dot ds is equal to the divergence of A to B. This is essentially the way I change from, using that divergence there, changing from this form to that form, the divergence of J rather than J. And then that's equal to, well, I won't rewrite it, it's equal to this thing. And then you say, then what you do is you say, well, what was that surface that you chose? Why did you choose this surface? Why didn't you choose this surface? I mean, and the point is, I could have, and the same, everything would be the same. So in other words, there should be, in front of all of this, any, okay? And same thing here, any. So if it's any, in other words, if you integrate this guy over one surface, the volume of one surface, or another surface, or another one, or another, and it always turns out that this left side is equal to that right side, then you can say that the integrand, this we can put the minus sign inside here, is equal to the integrand, right? I make this argument many times, that any is a very important word. So we come up with the idea that the divergence of this J, 3, as a function of time, is equal to minus the rate of change of the row volume of 3 as a function of time, dt. And I told you I would be connecting the J, the current density, with the charge that is essentially flowing, that's causing that current density, and that's the relationship. This is essentially the equation of continuity, right? Now, if we are at DC, in other words, I take a look at that surface, as much current is going in as is coming out. In other words, this is not really changing with respect to time. It is steady as a rock. Well, this is equal to 0. And then I come up with divergence of J. Well, if that's steady as a rock, then you don't need to use that symbol. You use this symbol, and it's equal to 0. And this is for DC current. Right? I mean, this handles the non-DC, but this is the one that we're in right now. This would be incompressible fluid. Okay, so now Maxwell accepted this. He accepted continuity, and continuity came from conservation of charge. So he accepted this, and we will see when we get to Maxwell's equations how important this equation is to the follow-on electric dynamics. Because it won't be this equation anymore. Okay? All right. I'll put the solutions out for the homework today out in my box outside my office. Okay? That's for homework? Okay. Yes.